Okay, so this is the last little bit of the HL content, indicators and pH curves. You can also think about this as saying titrations, titration curves. I'm going to use this as a quick review over indicators as well, so just keep that in mind. So in general, a lot of our indicators are really weak acids that dissociate partially, and then the unionized form, so the protonated form, is a completely different color than when it has donated this H+. And this happens at different pH levels. So we basically shift the equilibrium based on what pH the solution is at, and when that shift happens, the color change occurs, and that's how these indicators work. So now that we've talked about weak acids and bases, we now have a better understanding about how indicators work. So we use just Le Chatelier's principle to predict any color change. So as we add on as we add in H+, the equilibrium is going to shift to the left, giving us this red color. If we add in OH minus, so if we are adding in a base, what's going to happen is basically we are removing H+. So it's going to shift to the right and give us this blue color. So that's how these indicators work. They're really just weak acids and bases that we add in a couple drops of, just so that, not that so it's going to impact or serve as a buffer, but rather give us a color change indicator. So it lets us know where it's happening. So if it's acidic, it'll be red. If it's basic, it'll be blue. And that's just how indicators work. So we remember good indicators are going to have an easily observed color change, and they must change immediately in the pH range that we're looking for. So for example, if we're looking at methyl orange here, we are going to try to pick a titration that's going to change in that color. So it's going to go in this pH range. So somewhere from 3.5 to 5.5. So this would go from this yellow-orange color over here to this purple color. Very clear color difference. And that's what we're looking for. This change needs to occur at a spot that is of interest to us. So we need to have this change lining up in the spot where we think the equivalence point is going to happen or the end point. So we have to have this easily observed color change, and it must change immediately. So for an indicator to be good, it needs to be in the vertical section of a titration. So basically what we're looking for is where the change is occurring as quickly as possible. This is where we're reaching that equivalence point where our acids are now completely neutralizing our bases, or in this situation, since we're adding in alkali, this is where our bases, our OH group, has now completely reacted with the acid, and it's hitting that equivalence point. The indicator determines, this is all dependent on the pH that we are focusing on, or where we think the vertical line, that vertical change is going to happen, where that most drastic pH change is going to happen in a titration curve. So there are four types of of titration curves: strong acid, strong base; weak acid, strong base; strong acid, weak base; and weak acid, weak base. So it's just the four possible types that are the four possible combinations that you could possibly have with strong acid, strong base, weak base. The key point to notice is that the endpoints do not need to be neutral, and this is because, especially if you're doing weak acids or strong or weak bases, they're going to have a pH change, or they're going to have a natural pH that's outside of that range of 7. So that's going to be, if it's a weak base, when you have reacted all of it, you're going to have a pH that's going to be just a little bit higher, or if it's a weak acid, it's going to be just a little bit lower. And you'll see you'll see this as it comes up. So a strong acid versus strong base. You can see that it's basically a sideways, or it's basically an S. You have very little change, and this is actually exaggerated a little bit. This wouldn't be such a strong spike. What this titration curve would more look like would be something along these lines, where it's a more gradual change, and then when you hit this 7 area, it's going to be a huge change, and then it'll curl off a little bit more. And this is even probably too gradual, something more like that. The idea is that as you're hitting that equivalence point, you are having a huge change, a drastic change when you're getting close to there. Because this is pH, it's based off of a base 10. So when you're at this equivalence point, there are literally 10 H plus ions, and however many OH minus ions are needed to neutralize those out. Whereas down here, when you're at 1, you're talking about hundreds of thousands. So it's a base 10, and I'll explain more of that in class. So there's a very little pH change during the beginning. There's a sharp change as you're adding in. So as you're doing these titrations, you're going to be doing less than half a drop. We're actually going to run through these experiments after winter break, or sorry, after autumn break. And then there's a huge change up top, and then it's going to curl off based on what molarity of your strong base you're using, just like the beginning pH was dictated by the molarity of the strong acid we were using. So these would have different ending pHs if we were using NaOH of, let's say, 0.01 molar NaOH. That would just end at pH 12. So the ending pHs is just based off of the solutions you're titrating them with. So if we were going to pick an indicator, any one of these three would be good, just because they all line up in a section that is vertical. So what you could be doing then is just picking what pH do you want your ending solution to be at. If you wanted it to be at a little bit, like if you wanted it to be around 6, then you would pick methyl orange. If you were interested in it ending at about 8.4, then you would pick this one, litmus. If you were interested in a higher pH after you're done titrating, then you would just use phenolphthalein. But all of these would be fine. So an example of a strong acid versus a weak base. So we start off with our strong acid, HCl, and there's very little change. And we're adding in NH3 as we're doing this. So what is happening here is you still get this sharp change because you're completely neutralizing out the excess H plus ions that were created by the HCl. And then there's going to be a gradual curl off. And this is just because this is a weak base. It's going to have a pH a little bit lower than a strong acid, or sorry, a strong base. But, and this is also because you end up with, oops, H plus. Oh man, let me fix this. This is because what's happening up here is we were having these H plus ions. So this area represents this area of the graph down here, where we have an excess of H plus and we're adding in NH3, and it's turning into NH4 plus. So we're absorbing some of these H plus ions, and then as we hit this area here, we no longer have that. So what's happening is we've neutralized, we hit pH 7. I know it's not exactly 7, but it was as close as I could get. We've neutralized all the H+, and so now what we have is excess amounts of NH3, and they are going to be in equilibrium and create this NH4 plus and then OH minus group. And then this here is what's going to dictate how this equilibrium, how it sits, is going to dictate the final pH after all is said and done. So this is all about What's the weak base? If it tends to accept protons more readily, so if it lies on the product side of the equilibrium, it's going to have a higher pH. If it's not that good of a weak base, it's going to have a lower pH just because it's going to tend to lie on the reactant side. If we were picking a good indicator here, methyl orange would be the best choice just because it lies completely in the vertical region. Litmus would be the second best, but the problem is it starts to curl off near the tail end of the litmus change. So litmus will change color here, but by that time it's already been neutralized. What we're looking for is methyl orange is going to be completely vertical, and we're going to have a color change at when we're getting very close to that equivalence point. Indicators aren't the best way of measuring this, but it's traditional that we've used them. Now with the development of pH probes, we're able to get a lot more accurate results, but this is what indicators do. This is how they were and are used. Weak acid, strong base. Notice it's the same exact shape, but flipped over. Our strong acid, weak base looked like this. And this is the same thing but opposite, where we have a slow change at the beginning because we have this CH3COOH is going to be in equilibrium. It's going, since it's an acid, it's going to donate that proton into water, and as the OH gets added, we end up making ourselves a water group, and then we have this conjugate base. So what's happening is as we remove this, we start to eventually use up we shift the reaction to the right, and eventually we end up with this species only, with a CH3COO-. We have that sharp change where we got to be very careful, and then the curve is going to level off at a pH dictated by the strong base. Very, very similar. If we're picking the best indicator, we would be picking phenolphthalein because it lies completely in that vertical portion. So our color change would happen here, and this would be our original color. So it's going to change outside of that range. Weak acid, weak base. This is just a combination of the two. So there's no sharp change anywhere because these are both weak acids and weak bases. We're just combining two equilibriums. Eventually, when you get to excess, you hit a pH that is based off of the weak base you're using. And like we had before, our pH is dictated off of the excess of our weak acid, but you should see it's gradual each way. There's no sharp change at all. If we're doing we're trying to find an indicator for this, since there is no vertical region, there's nothing that's going to work out so well for this. If you had to pick something, you might pick litmus, but it's not going to give you a good result either way. There's no endpoint that could be detected, so you would probably use a pH meter and just plot the curve and analyze it from there. Okay, so then next up we have diprotic acids, or in this case, when this dissociates, we end up with Na plus CO3 2- H plus Cl, where these two are going to start to work together. This is my weak base, and this is my acid. And what you'll see here is a multiple change. So the first change is happening, so what I'm getting here is I have an excess of CO3 2-. Oops, I don't know why I put that one there. 2-. And right here I have a combination of HCO3- and there's going to be some CO3 2- as well, but not very much. Why do I keep putting the line there? Very, very little of this, to the point where it is negligible. pretend like it doesn't exist. Mostly this is going to be the species that you'll see here. And then as you finish your titration, as you add in excess HCl, you end up with what ends up being H2CO3, but that decomposes into H2O plus CO2. And then eventually you'll just add an excess H+. So this is where you're going to have HCl in excess. What you can look for here, though, is how many times is it curving down, and that'll tell you how many times you end up titrating a weak base. So I'm seeing one region, two regions, so I know 2 H pluses were needed. So this was once upon a time a diprotic acid. It can receive 2 protons. The first one you could use phenolphthalein because this is our vertical region. It's still not a perfect indicator, but it works out pretty well. It's going to be the best indicator we can get. In the second one, we could use methyl orange because we have this area here. But once again, at the same time, it's not straight vertical, so it's not going to be perfect. It's the best indicator that we could possibly use, though. And another example would be polyprotic. So this is a triprotic acid, 3 protons. Triprotic. And then what you can see here is this is going to be able to donate 3 protons. So you should be seeing 1, 2, 3 sharp changes. This is just going to let you know how many protons this thing was able to donate. The original pH would be 1.5. Our next pH would just be 4.4, and this is based off of this value would just be based off of the Ka of this is now a weak acid. This is strong. And the second it lost that first hydrogen, the next species is a weak acid. So this would be something that we would need to calculate using our Kas, figuring out how much H plus this is actually going to be able to donate in solution, and then calculate the pH back from there. And then H2PO4 is an even weaker acid. You should see that this is actually basic. It's such a weak acid that the conjugate base is stronger. It serves as a better proton acceptor than donor at this point. So that's why we talked about briefly in the SL, the weaker the acid, the stronger the conjugate base. So this is a conjugate base of H3PO4. And it's such a strong conjugate base that the pH actually lies above 7. And then we have an incredibly strong base. So this is, you should just be able to see this. I'm hoping that you'll see the 3 distinct regions, the 3 flat spots, if you will, and what those mean. Come with this in mind, and I'm going to clear up the last little bits on tomorrow, Monday, and we will go over how to figure out the halfway points and what the halfway points mean. Other than that, have a good day, have a good rest of your weekend, and I will see you tomorrow.